So we're going to look at some periodic trends. The first one we're going to look at is a trend in the size of the atom. So there's different ways to define this, and I'm not going to quiz you on these, but I just want you to be aware that when we say the size of an atom, well, it depends on how you measure that, right? So we can look at the non-bonding atomic radius. It's also called the van der Waals radius, and this is half the distance between adjacent nuclei in the atomic solid. So you have, say, krypton solid, and you look at the distance between two nuclei, and you divide that in half, and you say, okay, that's the radius of the atom. Or you can look at the bonding atomic radius, also called the covalent radius. So here you've got two bromine atoms, and they've bonded together. When they form a covalent bond, that pulls the nuclei closer together than they would be in a non-bonding atomic solid. So here, we're looking at half the distance between the nuclei, but here there's a covalent bond. For metals, we're looking at half the distance between two atoms next to each other in a crystal of the metal. Those are held together by metallic bonds. This distance is going to be smaller than that distance because of the bonding. So, you can quibble about all of this stuff. We care about general trends. And so when we talk about atomic radius, we're looking at sort of an average radius based on measuring the atoms in a variety of different forms and different compounds. And so it's not going to be exactly correct, but it's close enough. It's a more general term. It's generally going to be smaller than that van der Waals radius, than the non-bonding radius. When we want to know how long a bond is, we can approximate that by saying, for a covalent bond, that the bond length is the sum of the atomic radii of those two atoms bonded together. It's not exact, but it's good enough for lots of things. So there's a trend in atomic radius. Isn't that a crazy looking graph? How do we even look at this?
It's like a protein.
It's like all over the place, like the weather maybe, up and down and up and down. So the atomic radius increases as we go down a group. So if we look at the alkali metals, we're just going to look at lithium, sodium, potassium, rubidium, cesium. So here's the radius in picometers, and we see that as you go down the periodic table in a column, the size gets bigger. This makes sense, right? I mean, cesium, what's its molar mass? 132.9 grams. Versus sodium, 22.9 grams, you would expect it to be bigger, right? That makes sense. What's really important is that we are adding electrons to increasingly larger principal levels. And just, like the Bohr model is helpful in that we understand that n equals 1 is smaller, n equals 2 is bigger, and they get bigger and bigger as you go out. So cesium has electrons in the sixth principal level. It's going to be larger than rubidium that only has electrons in the fifth. Yes?
Does the radius between the next number get smaller?
It does. Yeah, so if you look at this, the jump between lithium and sodium is large. The jump between rubidium and cesium is smaller. And part of that is because as you go out, the change in energy and the change in distance from the nucleus of each subsequent level, the difference is smaller. If we look at the other end of the periodic table, the noble gases, we see that same trend: helium, neon, argon, krypton, xenon. They're getting larger as you go down the periodic table. Now, when we go across a row, things get different. So like the second period lithium to neon. That's not what we would expect, right? Neon is a more massive atom. You would expect it to be larger, but it isn't. It's actually smaller. We see that atomic radius decreases as we go from left to right. What? Okay, there is a decent explanation for this. This one makes sense. Going down gets bigger. So that one's okay. Why do they get smaller as we go across? It has to do with shielding. So we've got electrons being attracted to the nucleus, but also being repelled by each other. Those outer electrons get shielded from the attractiveness of the nucleus by the core electrons. And so they don't experience the full strength of the nuclear charge. So here we're looking at lithium again. We looked at this picture earlier. The lithium nucleus has a positive 3 charge. There are 2 core electrons and 1 valence electron. The valence electron is in the n equals 2 level, and these are in the n equals 1 level. So these are going to be closer to the nucleus, and they're going to shield that electron from some of the attractiveness. Okay, so the nucleus here has a jacket on, and you can't see its loveliness, right? We can do kind of a rough calculation of that. It's called effective nuclear charge. You take the charge on the nucleus and you subtract the number of core electrons. So there's a positive 3 charge here, but there's 2 electrons shielding it. So we subtract those off and we get an effective nuclear charge of approximately 1. There are more exact calculations, but we don't need them, so we're going to stick with this really simple one. So effective nuclear charge, the net charge that is experienced by a valence electron. The valence electrons are the ones on the outside. They're the farthest away. Those are the ones that determine the size of the atom. So the effective nuclear charge equals the actual nuclear charge minus the shielding by the core electrons. So let's look at the effective nuclear charges of nitrogen and argon. Jeez. Okay, so nitrogen, how many valence electrons does nitrogen have? 3. So it's got 3 valence electrons. How many core electrons does it have?
7.
Well, how many electrons does it have? Nitrogen. It's got 7, and 3 of them are valence. So how many are core? 4. 4 core electrons. Or you can do the Lewis electron configuration. What am I doing here? No, it's not 3, it's 5.
Yeah.
You guys are leading me down the garden path. Just seeing if you're awake. No, 5. There's a total of 7. There's 2 core electrons. So you can draw the Lewis, not the Lewis structure, that's later. Electron configuration, and we see 2 plus 3 is 5 valence electrons and 2 core electrons. So to calculate the effective nuclear charge, Z effective, we're looking at the charge on the nucleus. What's the charge on the nucleus for nitrogen? 7. It's got 7 protons.
7 protons.
Right? 7 protons, 7 electrons. So the charge on the nucleus is 7, and we're going to subtract the number of core electrons. So subtract 2, and so we get an effective nuclear charge of 5. Because if we draw a very simple kind of a Bohr model of nitrogen, here's n equals 1, and we've got 2 electrons there. Right? And n equals 2, we've got 5 electrons. 1, 2, 3, 4, 5. So any one of these electrons sees the plus 7, but it's shielded by those 2. So that reduces how attractive it is. So this has an effective charge of 5.
Is that 5 always effective every a second at a time? Because I know
This is an approximate. It's just approximate. Yeah.
So the more shielded the atom is, the bigger its radius
Yes.
is going to be?
Yep, exactly. The more shielding there is, the bigger the radius. So let's look at argon. I'll change colors here because this is getting confusing. So argon. So argon is element number 18. So we've got 18 protons in the nucleus. We have a total of 18 electrons. How many of those are valence electrons? What group is it in? It's in group 8, right? 8 valence electrons. How many core electrons? 18 minus 8, right? 10 core electrons. Or you can draw all this out, whatever. So the effective nuclear charge then for argon is the charge on the nucleus, which is 18, minus the number of core electrons. So 10. So 18 minus 10 is 8. The electrons in argon are experiencing an effective charge of positive 8 compared to an effective charge of positive 5 for nitrogen. And this goes back to Coulomb's law also. Coulomb's law is proportional to Q1, Q2 over the radius. So for nitrogen, we've got a negative 1 electron and an effective nuclear charge of plus 5 over some radius. And for argon, it's a negative 1 for the electron and a plus 8 for the effective nuclear charge on the nucleus.
Because it's a negative 1, is there going to be a time where you can do compounds? Like, figure out all this with a compound?
No, we're not going to do this with compounds. Yes?
What did the negative 1 help?
Yeah.
Okay, this negative 1 is the electron. So Coulomb's law says the force of attraction or repulsion between two charged particles. Q1 is the charge of one particle, Q2 is the charge of another particle. So we're looking at one of these valence electrons, its attractive force to the nucleus. So if there wasn't any shielding, it would be negative 1 times positive 7. But because of the shielding, it's reduced to 5
So the negative
over
1
R.
is like constant.
Yeah, all electrons have a negative 1 charge. We're looking at one electron attracted to the nucleus. But the charge that it sees depends on how many core electrons are in the way.
How much it's being pushed over?
Okay? So what happens, and quantum mechanics explains this, as we're moving down a column, the principal quantum number of those valence electrons is going up, so we get larger orbitals and larger atomic radii. As we're moving across a period, the effective nuclear charge is increasing. It's increasing as you go across because the number of core electrons is staying the same, but the number of protons in the nucleus is increasing. So you've got a higher effective nuclear charge. That's going to pull those valence electrons in. You get stronger attraction between the valence electrons and the nucleus, so they're going to pull in closer. As you go across, it's going to gradually get smaller and smaller. And that's why neon is smaller than lithium. Picture here? No. So let's go back to this picture. So as we go across, the effective nuclear charge is getting larger, and so the radius is getting smaller. There are exceptions to the trend, but in general, the trend is pretty good. So we should be able to predict which atom in each pair is larger. How do we do that? Look at the periodic table. So tin and iodine. So I'm going to draw just a little piece of the periodic table here. So there's tin, and here's iodine. They're in the same period. So which is going to be bigger? Well, you would think that iodine would be bigger because it's got a larger mass, it's got more protons, it's got more electrons. But it's smaller
Valence electrons are more attracted.
because it has a higher effective nuclear charge than tin. And that higher charge pulls the electrons in tighter.
So it makes it smaller.
So tin is larger. He's getting it. It's awesome. It's fun when it makes sense. Germanium and polonium. I really should have a periodic table here. We just need their relative positions. So if polonium's down here, germanium is up here. Well, here we've got a diagonal going on, right? So as we go across this way, things get smaller. So that trend would predict that polonium is smaller than germanium. But as we go down, the trend says they get larger. So we have opposing trends. Well, if we're forced to pick, we have to decide which of these has more impact. The increasing of the principal energy level or the increase of the effective nuclear charge. The higher principal level is going to have more effect. So polonium is larger. This trend, the vertical trend, is more important than the horizontal trend.
Why is that again?
Because as you're going down, you're adding new layers of the onion skins, right? And so they're farther out. Going across, it's just you've got a slight contraction of the existing level. And so that's a smaller effect than adding new layers.
All right.
That make sense? Yeah.
When I said this, what I was thinking doesn't make sense.
Okay. Chromium or tungsten? W is tungsten. That makes sense, right? Because its original name was wolfram. Wolfram. You've heard of wolfram alpha? Wolfram alpha? It's a website that'll solve your math problems for you. I shouldn't have told you that. So these guys are easy. They're vertical. Which one's bigger? W. Tungsten. Well, yeah, but a lot of these things have two names.
So what would be the tipping point in where the horizontal would actually be more of effect than the...
Okay, so that's a good question. So here, these guys are only separated by two columns, right? There's just one column in between. This is just two columns over. So then it's only a little bit of the horizontal, right? And it's an equal number of squares going down. So there I'd say, yeah, you can definitely predict. Now, if you've got, instead of here, you've got one over there, that's going to be tough. And I wouldn't ask you to do that on an exam. Yeah.
Is there a possible way to figure that out? Or?
Well, you can go and look at the table, yeah. Yeah, so if we're looking at like phosphorus versus iodine, well, going across things get smaller, going down things get bigger. And the going down trend is more important. But now if you're comparing this with sodium, which is way over here, we've got a whole bunch of going across happening and only a little bit going down. And so there, the going across was more important. Sodium's actually bigger than iodine. And I would not expect you to be able to predict that. So we'll keep with things that are either in the same row or column or close together. But you should be able to predict that. It is just really helpful to be able to predict just generally what's going to be larger. Okay. Oh, I skipped this by accident. What about the transition metals? They're kind of squirrely. Well, as we go down the column, the trend holds pretty well because you're adding principal levels. But when you go across the main group, across the transition metals, in the same period, the atomic radii are going to all be approximately the same size. There's very little difference, and the trend is not very good, and the effective nuclear charge is also approximately the same, because the valence shell is the S2, not the d electrons. So let's go back and look at that. Oops. Well, yeah, let's look at this. My iPad's so confused. Okay, there we go. So like, here's the period 4. What? Period. I'm not moving. Period 4 transition elements right here, right? So it goes down, it comes up a little bit. There's not a real solid trend there. And period 5 is even a little worse, right? So what's going on with that? Come on. I'm waiting for my iPad to change the screen. Oh, well, I guess I can do it this way. Okay, so let's look at scandium. I'm trying to point to scandium. There's C, right there. Okay, so in its electron configuration, it's got 4s2, 3d1, right? What are the valence electrons? 4s. It's got 2 valence electrons. If we look at zinc, okay, just imagine I'm pointing at zinc. If we look at zinc, zinc is 4s2, 3d10. What are the valence electrons? 2, the 4s2. Because the 3d, even though they're being added after the 4s electrons, they're not valence electrons. So scandium and zinc have the same number of valence electrons. And so the difference with effective nuclear charge doesn't matter very much. Yes?
Why isn't the 3d10 the valence electrons?
Because valence is the highest principal energy level.
Yeah.
And 3 is smaller than 4.
Oh, I thought you said it was at 2s.
Well, it's 4s2 for potassium and calcium. 4s2 and then 3d10 or whatever.
Yeah.
The 4s2 electrons are the valence electrons.
The D is, even though it's...
The Ds are considered core electrons.
It's minus 1, so it goes up 1.
And so what's happening as you're going across there, you're adding core electrons as you're adding protons, and so the effective nuclear charge really doesn't change at all. So they're just kind of hard to predict. I'm hungry too. Okay, we did that. Okay. So I think we finished